Okay, so we are still in this chapter number 3. We are talking about memory management, and we have seen a bunch of page replacement algorithms. Last time, I guess we stopped at this point. I introduced the idea of working set. We talked about this, and if you make a small, very little review of what we did last time, working set, that's the definition of the working set. It is the set of pages used by the k most recent memory references. That's what we said about the working set. Did we start the attendance? Yeah. Okay. So the working set is the set of pages used by the k most recent memory references at time t. So we looked at it last time. We said that it is monotonically increasing, and if we allow very large k's, wkt will be the size of the process itself. But we are not interested in the size of the process. We are interested in the k most recent memory references. If we keep k sufficiently large, then that means that I keep that many pages in my memory, and because of the locality of the reference, that working set is enough for me to work with this process. So important thing is that find the k value, okay, good a k value, and try to keep that many given by the k, okay, try to keep that many pages in my memory for this process. That way I want to any trashing, okay. So remember, trashing is a bad thing. Trashing says that if you keep swapping your pages back and forth when you switch processes, or the same process is loading a page, then after a very small amount of time loading another page and another page, is called trashing. So by keeping the working set of the program, all the pages needed of the program or a process, then I will prevent this trashing and I will have a very efficient system. That was the idea. And we introduced this idea of the working set page replacement algorithm. Okay, we said that okay, let's track the last memory references. So remember, with the least recently used algorithm, with the help of the special hardware, with the least recently used algorithm, we used to keep the last memory references, but that's not possible if we don't have the hardware help. Instead, we will track the pages referenced during the last seconds. So how are we going to do that? We have our clock interrupts, okay? Whenever the clock interrupt happens, we are going to say that, okay, these pages were referenced in the last, from the last clock interrupt to the current clock interrupt. So we will, for each page, we will keep a virtual clock field, and at every clock interrupt, okay, we will update that virtual clock field. That's not a real clock, actually. I am just counting the number of interrupts, okay. I'm just counting the number of interrupts. Every time interrupt happens, I increment the virtual clock field by 1, and I put that number into the special fields of the pages, and at each pick I update the clock field of all the pages if that page is referenced, okay. And that's the basic idea. If I see that the page is not referenced for the last few seconds, for the last few clock interrupts, then I can discard them if they are not in the working set, if they are not accessed for the last seconds maybe. So that will be, last seconds will be my k value, okay. So here is an example. We looked at this last time. remove this. Okay, so every page, this is my page table. At each page I have the R bit. I know these. Okay, these are supported by the hardware memory management unit. Memory management unit makes these R bits 1 whenever that page is referenced. And I have my virtual clock field. Okay, this virtual clock field indicates the last time I have referenced that page, and I keeping this virtual current virtual clock time as a global variable somewhere in my memory, in my kernel space. Okay, in my kernel space. So that's basically the data structure that I keep, and this will be my main algorithm. At every clock interrupt, okay, if R is 1, I scan this page table. At every clock interrupt, I scan this page table, okay. If the R bit is 1 for that page table entry, then I write this clock virtual clock time to this position. If R is 1, then I update these positions. If R is 0, that means that page is not referenced. I don't update that value. So that page gets old. Okay. If R is 1, set the time of the last user current virtual time. If R is 0, okay, then I am not going to update that value. But if R is 0, and then I can calculate the age. For example, the difference between this and this, okay, 2200 minus 2200 minus, what should I say? You know, but yes. Well, maybe I shouldn't. Well, I like it, but I don't like it then. Okay. So 2200 minus 1200. If it is above some threshold, then this page is removable. Okay. I can mark that page as remove that page. Okay. So in this algorithm it says that if that page is old enough, then remove it. Okay. If that page is not that old, then keep that page. Okay. So at every clock time, at every clock interrupt, I can make a decision. So even though I have space, even though I have space available, I can say that I am going to remove this page because this page is old. Nobody is referencing it. Okay, and I'm making all these decisions during the clock interrupt time. We are not talking about the page fault time. Okay, when the page fault happens, you will have to load one page from the memory, and if you don't have any pages available, then you have to replace one. But this one keeps doing the page removal all the time during the clock interrupt. That's why I say that doesn't matter how many processes I try to run on this computer, I always have some memory available. I have lots of processes running. Okay, I have lots of processes running like these, but doesn't matter how many processes I am running. Okay, it will always try to keep, okay, like this much of the memory available for me. Maybe at the beginning, maybe if let me show you this. Okay, I am loading a new program. I am loading the Chrome. It will, okay, get some pages first. Okay, so my Chrome has reached its working set. Okay, I don't think that I have loaded in. Let load another one. Okay, I am loading another one. So it is causing lots of page faults and page faults and page faults. It is loading and loading and loading. Okay, doesn't matter. What should I load? One more. Can I load? Do I have anything expensive? Maybe load Word. Word. Is it loading? and yeah, did you see that? It loaded Word, and after a while, when the Word reached its working set, my available pages increased a little bit. It says that, okay, nobody is using these pages of the Chrome and maybe the Edge. Okay, let me try to load Excel. I guess it is loading right now. Is it? Yeah, it increased a little bit, now it is dropping back. And if I try to load lots of pages, okay, blank document, etc., get this one out and load this one, and from the Chrome maybe load the same thing again, load lots of, maybe this one. Yeah, I think it's going to load it. So it always keeps it loads some, and it realizes some of the pages are not used, and it decreases, and it tries to keep some pages available here. So this is called demand paging, and the demand paging and the working set algorithm works very well. Okay, so because it removes some of the pages that are not used at all. So let me get rid of these and this and this and that, right? So I lost lots of pages, so many pages are available now. So as I said before, this happens before the page faults happened, because at every clock time I am measuring the ages of each page. Okay, I can mark them as these are removable. So it depends on this this tau time, this threshold time, and this threshold time is operating system dependent, and sometimes it will let you, as a user, as an ordinary user, sometimes it will let you choose your threshold time. Sometimes the system administrator can choose this threshold time. How old pages do you want to keep in your memory? Okay, so that's the working set algorithm. It happens this way. So this is how you remove your pages, how you keep your pages. Question is, if I don't have any pages that are old enough, okay, if all of my pages in my memory are young, okay, they are not old enough to be removed, okay, I need a new page. So what are you gonna do in that case? You will have to remove the page that is the youngest, that is the oldest, sorry. Okay, so you will have to remove that is the oldest, even though its age is smaller than this threshold value. So that means what? You are removing one page from your working set, and that's a very, very bad thing. Why? Because if you remove a page from your working set, that means that you are going to cause trashing. You need that page, okay? You need that page, and you are removing it, and you know that in a few minutes, in a few moments, sorry, not minutes, in a few moments, very short amount of time, you will need that page, and you will end up loading it back again, and you don't have the memory, so you will have to remove another young page, and that will cause trashing. And trashing is bad, but working set algorithm is good enough to let you know that this is going to cause trashing. Okay, knowing that something is going to cause trashing is a good thing, because you will let the user that I will start trashing the memory, okay, the pages. So what are you going to do? How would you prevent trashing? One, okay, remove one of the applications that are using memory, loss of memory. Okay, you would say that I can't run this many applications. So what are we going to do? I am going to stop this application so that the others can run. The other solution might be swapping the whole program to the disk. Okay, well, that's not a very good solution, because you will need to run that program anyway. So so you will load it back to the memory. But removing one of the applications is a good idea to prevent trashing. Okay, so working set is a good algorithm. Let's look at the variation of working set. Okay, it's called working set clock. It's the same idea as the before. Remember the clock algorithm? Clock algorithm is the second chance FIFO with a circular linked list, remember? If I use the same data structure, I will keep having a pointer, okay? And this pointer will point to a page in my page table. And this pointer runs in a circular list. Okay, this is what happens with the clock algorithm. Have a circular linked list of page frames. At each page fault, okay, we are talking about the page fault, check the page R and time. So I am looking at this page. I am checking the R time and R bit and time of last use. If R bit 1 is okay, I can't, okay. If R bit is 1, the page is incurrent and can't be discarded. I advance the clock hand. If R is 0, then I check its age. If it is old enough, then I can replace that page. Okay, this happens when, okay, when there is a page fault. If it happens when there is a page fault, okay. If there is a clock interrupt, I do exactly the same thing. I scan all the pages, okay. I scan all the pages one by one, and update their current time if their R bit is 1. Question: what do I do after I do this? Do I clear the R bit or I keep the R bit? During the clock interrupt, okay. During the clock interrupt here, okay. At each tick, update the clock field or the virtual time field that R bit is set. What do I do with the R bit? Do I make it 0 or do I keep it as 1? I should make it 0, right? If I don't make it 0, then R bit stays as 1, okay? That means what? At every clock interrupt, I will update its virtual clock time, so that page never gets old, okay? So the R bit, like we did as before, R bit is cleared at every clock interrupt. Other than that, I would update the virtual clock time for each page. And working set clock is no exception. The only thing is that during the page fault, I scan these pages. Okay, I am not going to replace this one because okay, this R bit is 1. This one I am going to check if R bit is not 1. For the last clock interrupt, nobody used it, but is it old enough? How am I going to know that? You would check the difference between these two. Okay, if the difference is large enough, then that means that page is old enough. I am going to replace it. That's the algorithm for replacement. But again, as I said before, this with the demand paging, this rarely happens because demand paging always keeps some pages available. See, 50% of my memory, almost 50% of my memory is available. So whenever a page fault occurs, okay, the system has lots of available pages to use. It just, without doing any replacement, okay, just say that I am going to use this page because this page is empty. Okay, that's the beauty of the demand paging, and this demand paging and the working set clock algorithm is very compatible. That's why we usually use the working set algorithm. Okay. So what happens with the modified pages? We never talk about the modified pages. We kept talking about the virtual clock field and the R bits. How about the W bits? modified pages, okay, W bit or the M bit modified pages. If W is 0, then you don't have to write it back to the disk. You just replace that page and use it. If W is 1, okay, it has to be written back to the disk, okay. Don't wait until it is written. You just ask the operating system to write it to the disk, and you keep scanning, okay, your pages to find the page old enough to be replaced and it is not modified, okay. You ask the operating system, you need to write this to the you need to write to the disk, and I will try to find another page that doesn't need to be written to the disk, and you keep scanning. This page will eventually will be written to the disk, and that will be available for some other process to use it. So again, nice features of this algorithm. Okay, I don't have to wait until that page is written. I am just scheduling it. An operating system, whenever it finds time, it will write it to the disk. Okay, that's the modified pages. Of course, if all the pages that are old enough are modified, then this circular linked listing is going to be scanned from the back again, and I will have to wait until a page becomes available. But that's a bad case, but I have no other choice. Okay, I have no other choice. Okay, so that's what I'm saying. Okay, what happens if the clock hand circles? I keep circling it until one page becomes available. Okay, until one page becomes available. Again, if I see that no page is scheduled to be written to the disk, all pages are referenced, and they are all young, they are not old enough, then I have to pick a random page to use. Then that's going to be, again, that might cause a trashing. That's a bad thing. So that's it. That's the old algorithm that we have looked at so far. This page nicely summarizes them. Remember this one. Optimal. Okay, what does optimal say is that? Okay, optimal says that I am going to look into the future. I know the future. I am going to replace that will not be referenced longest. Okay, it is not possible to know it. It is not implementable. But on simulation systems, I know the optimal values. I can use that value to measure myself. Am I doing close to the optimal, etc. So this is not runnable in the real time, but in the experimental world, of course, I can do whatever I want. And are you not recently used? Okay, these names are actually nice. Okay, say that not recently used. Not recently used does not mean, okay, other than this, everybody, okay, this one looks into the future. Other than that, they all look at what happened in the past. Okay, by looking at the past, I am trying to guess what's going to be in the future. And how do you say that I am going to see who is not recently used? Okay, not recently used means, okay, okay, but the thing is that it would be nice to know least recently used. Okay, it is not recently used, but least recently used. Maybe some of them are used recently, but they are used in a very, very minimal amount of time. So least recently used. So I can't do that. This is expensive. How about this not recently used? So what am I going to do? I keep looking at this RBIT all the time. RBIT is going to tell me if that page is used or not recently. Not recently used algorithm. Remember, for class algorithm 0001110, etc. So it's a very crude approximation for least recently used. Then we have this FIFO, first in first out, the oldest page. This doesn't care about the RBIT at all. This doesn't care about if the page is referenced or not. That's not a good thing, but the second chance algorithm is a better one. And the clock algorithm is the same as the second chance algorithm, but it uses a circular length list. Okay, it is better than, of course, the FIFO and the second chance, but performance-wise they are the same thing. This one is only more efficient. Then this one we liked a lot, least recently used. Again, it is good. It says that if a page is used in the least amount of time among all the pages available, then I'm going to replace it. But this one requires, remember, a special hardware. For each memory reference, you need to keep the time of the reference at the page level. And we say that not everybody is that lucky to have that kind of hardware. How about not frequently used? Okay, it is not recently used, but not frequently used. Not frequently used is, remember, we keep using again virtual clock time, and we say that I am going to measure how many times you have been used recently. But if you use this NFU directly, thank you. If you use this NFU directly, did everybody sign this? Okay, come here and sign it. Just one person? Okay. NFU is nice, but the pages doesn't get old, okay? I keep measuring how many times they are used. So that value is not very useful for me, but when I introduce this aging idea, the pages get older and older, then that's a good idea. Then finally, we have this working set idea, okay? We said that for the working set, we try to keep certain number of pages for that process in my memory, and that number depends on the process itself. Okay, so those are the algorithms for the page replacement. Paging is still, I mean, since it's an invention from the 1960s, we keep using paging. Okay, we didn't give up on paging. We are still using paging, and in fact, there's page faults and the page fault interrupts, handling the page faults, number of page faults, and etc. They are all still valid terms for all the operating systems that we have. Okay, did I miss anything? Yeah. Okay, good. Thank you. Okay, so that will be it about the paging algorithms, and we are going to look at some memory management design issues. We have skipped lots of details. We are going to look at them. For example, we didn't talk about how about the processes. How about I have many processes, okay, and these processes have their own problems and etc. We are going to look at them. We are going to look at the how do you choose your page size, etc. Those kind of design issues. If you don't have problems. Okay, then I will move on then. Okay, one criteria that I am going to look at is global versus local allocation. This is a problem. Okay, let's say I have two processes running. Okay, process A has certain number of pages in the memory it is being used, and process B is doing the same thing. It has certain number of pages, and there is a process C. So I have 1, 2, 3, 4, 5, 6 pages for process A, and 7 pages for C, and 3 pages for, I guess, process C. So the thing is this. Let's say process A caused a page fault. Okay, it needs a new page. MMU said to the operating system that MMU caused an interrupt, said that process A caused a page fault. The page that it needs is not in the memory, so make a page loading for me. An operating system looks at this picture and says that, okay, I need to replace a page. All the pages are full. What am I gonna do? Should I replace one of the pages from this 6 pages of process A, or should I choose one of them globally? That's the problem of local versus global. Should I replace the pages based on the local decision over the pages of A, or should I do it globally? If I am doing it locally, I will choose one of these 6. In this case, I am going to choose this A5 and replace it with A6. If I do it globally, maybe I will choose one of the old pages of process B. Okay, process B. Which one is a better solution? Global or local? And of course, as always, there are pluses and minuses for each solution. If I do it locally, nice thing is that I know that definitely process A will keep using 6 pages, and process B will use 7 pages all the time. That will be it. But the local allocation misses this part. Local allocation ignores the fact that sometimes processes shrink. They don't need much memory. Sometimes they get larger. They need lots of memory. Okay? So if I use the global allocation policy, then my processes can get larger and smaller, right? So that would be a nice thing. Okay? That would be a nice thing. So if a page replacement affects only the current process, we have a local policy. Otherwise, we have global policies. So the choosing happens this way. The global policies tend to work better. The globals, they tend to work better. And if we use a local policy, when the working set grows, okay. Since with the local policy, if my working set grows, if I cannot fit into the 6 pages, then I will cause trashing, even though some memory is available. Okay, so because I am making my decisions locally, that's not a good thing. So that's why we like global policies better than the local ones. Okay, of course, a process should never grow to a position where it uses up all the pages from all the other processes. We have to be careful about this, but usually the global policies are more efficient. Okay, so with the global policy, you need to decide how much memory to allocate to each process. Maybe there should be a minimum size for each process. Okay, maybe there should be a minimum size for each process. Maybe you should say that, okay, the working set minimum for this process is this much, and I am not going to let anybody use the pages of this process if I am below that threshold. Okay, so this is an idea where we can use this with the global versus local allocation policy. Always monitor the page fault frequency, PFF. This is a very critical number for operating systems to keep your eyes on. Okay, PFF, page fault frequency. You measure how many, okay, if this is time, and if this is my PFF, okay, if this is my page fault frequency doing this, okay, keep looking at this graph for all the processes. If this is kind of going down, that's fine. It is doing okay, because I mean, at the beginning of process creation, I know that a process will cause lots of page faults. because of the demand paging. Whenever a page needed, it causes a page fault, and I have to handle it. At the beginning of the process creation time, PFF number will be high, I know that. But after a while, it should get smaller and smaller like that, okay? So I need to keep looking at this number, PFF. And how do you measure the PFF? Of course, as the operating system, you keep track of how many page fault interrupts you get from a process in the process table, okay? And if a process is causing PFF, large PFF values for a long amount of time, that means what? That process is causing trashing, okay? It keeps replacing the same page over and over again. Okay, that's not a good thing. Okay, so a process with a high PFF Gebze, that means what? If that process is causing trashing, maybe I should give more memory to it, so that its working set fits into the memory. And if a process with a small PFF, if I see such a process, that process is running, but it is not causing any page faults, then maybe I should deallocate some of the pages that it is using. Maybe I should make its working set size a little bit smaller. So these kind of decisions are done dynamically by the operating system, okay, with the help of the idea of the paging. Okay, good. Any questions on this? Global versus local. So you like to keep, you don't want to eliminate all of your page faults for a process. That means what? If a process is not causing any page faults, that means that the whole process is in the memory. We don't want that, okay? Of course, if there are no other processes, that's a good thing. But if some process is causing lots of page faults, and in some other process is not causing any, then that means that one of the processes has small number of pages, the other one has a large number of pages. Okay, so you like to keep your page faults per second between the two threshold values, A and B. Anything above this is called trashing. Anything below this is caused that process is using too much memory. Okay, you need to keep your page faults between two intervals, between two values. Okay, and these values are operating system parameters, and sometimes operating systems will let you select these values A and B as the system administrators. Okay, and how do you measure the PFF? Okay, and count the number of page faults per second. As I said before, if this is my time and this is PFF for each one, if I get a page fault frequency like this, okay, if I take the average of whole thing, it would be like that, right? A constant line. Taking the average of whole thing is not a good idea, because it doesn't tell you anything about the history of it. Am I getting better? Am I getting worse? So that's why we don't take the average. We take running average. What is running average? Okay, remember what we did with the aging. You give more weight to the recent values of PFF than the older value of PFF. Okay, it's like this. You say that my time estimation for the t value, maybe PFF t value, maybe it should be alpha times p. I'm going to make it f. Okay, p. PT is going to be alpha times t minus 1 plus 1 minus alpha times pt. p minus 2, okay, and alpha is going to be between 0 and 1, and of course alpha has to be in this case greater than 0.5. So I am giving more attention to the recent times, not the previous times. That's called the running average, right? That's called the running average, and that's how I measure the PFF. So don't keep a graph. Graph is too complicated, because I keep these numbers in my page table, right? Page table, dealing with this page table has to be done very, very carefully, because you deal with the page table during the clock interrupts, during the page fault handling. You can't spend too much time on it. Okay, those are critical times. Also, fitting this graph, putting this graph, the whole graph, inside your page table takes lots of time and takes lots of space. I don't want to do that either. So just keep a number, the recent PFF value, okay? But that PFF value should be a running average of the PFF, instantaneous PFFs of the process. Okay, that's how we measure the PFF values. Okay, let's look at, remember our algorithms, the FIFO algorithm, second chance algorithm, LRU algorithm, working set algorithm. Let's see how we can analyze these algorithms in terms of their allocation policies, global allocation or local allocation. So I am going to check each one by one. Okay, optimal, I am going to skip it. NRU, would it work with global and local algorithms? Equally fine. I'm going to look at this question one by one for each of the algorithms. That's what I'm going to do. Okay, so algorithms such as LRU and FIFO work with either global or local allocation policies. Remember the LRU least recently used? It says that who is being used least, okay? Or FIFO is chooses the oldest one. So I can do this either on a global basis or a local basis, because for the FIFO I am looking at the oldest page. I can do this for the whole pages, or I can run my FIFO. For the for each process separately, or I can do this LRU for each process separately. So this LRU and FIFO are compatible with both local and global allocation policies. That's fine, but the thing is, the algorithm that we like most, this WS clock, working set clock. Well, working set clock says that I am going to compare the age of each page by looking at this threshold value. The threshold value is a global threshold value. Okay, so and the thing is that working set is defined for each process. Okay, so I need to make this run for local with the local policy only, because working set tries to measure the working set for each process. Okay, so the working set and VS clock are local only. That's not a good news, because we like the global policies better than the local policies. So there is no such thing as the working set for the entire system, because that wouldn't be meaningless. So what am I gonna do? Maybe I should rely on allocation policy for global effects. What do I mean by that? Okay, each local working set decision should know that there are other processes running. So if I need to increase my working set size, then I'm going to ask the operating system to give me more memory. I need more memory because I now keep discarding my pages in my working set. Or I should inform the operating system that, okay, I am fine, I'm not causing any page faults, and maybe I should give some of my pages to the operating system. So I need to modify my allocation policy in some way so that this VS clock, which we like a lot, works with the global allocation policy, because we like the global allocation policy better than the local allocation policy. Okay, good. Any questions? Okay, let me move on if there are no questions. We did not talk much about swapping. Okay, well, at the beginning we talked about it. We talked about swapping the whole programs between the memory and the secondary storage. Okay, we talked about those, but we didn't come to this idea after that. Maybe we should talk about it a little bit, but before that I need to take some break. Okay, let's be here around 11:33. Okay, 15 minutes.
Sesinin sesinden tanımıyor. Bir defa birinin sesinden tanımıyor. Nasıl demek belli oluyor sesin. Kendi güzel sesi. Ben Ömer'i karşı etmiyorum ki. Kendileri müziklerini tanımıyorum. Onu karşılamamız lazım. Sen bunu tanıyor musun? Tanıyor. Evet tanıyorum. Ama hem böyle tanıyorum. Kimse tanımıyor. Biz ne yapacağız? Evet ben de onu düşünüyorum. Onu yönetmek lazım. Sistemden zaman yönetemiyorum. Senin bir yöneticiye ihtiyacım. Bu arada sıcağım hasta yani.
Diyordu ya hoca 11 hafta boyunca isteyeceğim falan da. Kaçıncı haftada?
9 bitiyor. 8 olabilir. Ben yazın böyle konuşmamız gerekiyor. Ne konuşalım? Ne konuşalım? Rapor yazmamız gerekiyor. Bir anlasınız değil misiniz? Her gün atmasınız. Ya bilmiyorum. Bazı gruplarımızda neyi falan. Evet. Zaten sizin arkadaş da. Aslında gelsiniz. Bazı şey geldi ya.
Geldi mi?
Bir şeyler geldi mi? Hemen geldi. Okul değil. Şu bana bir şey yok. Ya onlar galiba bir şey evlenmiş. Kurban bağlı. Bir şey var. Böyle şey var. Net durum kısımda. Şeyde biz küçük bir izin mi alsak? Çocuktan geldi. Biz ya şey değil de zaten bence çok okuyacak. Okuyacağım düşünmüyorum.
Şey demiş ya kendiniz okuyun.
İyi ben kendimi izlemiyorum. Ben hocam kemer öyle.
Ya ben şey yapmışım 3. soruda. X'ler de yerine ters almış.
Evet ya o çok...
Nasıl bir şey lan? Ters olmuş dedim ki hocam ters yazmışım ben ama işlemler doğru çıkmış. Lütfen bize aferin.
Verim bu arada.
Ben de verim ya.
Vallahi.
Çok rahat.
Kim okuyor? Bize boşa karı taşıyor. Çok iyi, çok iyi. Ben var ya, abi mükemmel öyle. En sevdiğim aslında.
Serdik, sen şuna kaçırdın. En sevdiğim arkadaşım sensin.
Karşılıklı bak.
Yaptın mı ödevi?
Nasıl
yaptın? Ben gönderiyorum şimdi.
Yaşlarını ben sandım şimdi ya.
O zaman önden bu oyun gitti yani. Önden bu oyun gitti.
Varsa varsa ya. Ama cidden çok saçma. Sırf o yüzden sıfır vermesin.
Ne oldu? Kaç değil mi?
Şey almıştım bize söyleyin.
Ne oldu? Ha şey diyorsun ya.
Ben anlattım ama.
Ama o çok açıktı be PDF'de.
Ama öyle anladım. Ya öyle anladım. Bak sen de kelime yapmıştın işte.
Kelime
Yerleme yap. Koyma yerleme.
orada da yapın.
Orada bir şeymiş. Required'miş. Bakıyor aslında
Kelime falan.
Bir de bir şey diyeceğim. Hoca input dosyasını attıktan sonra böyle az kişi girmeye karar verdi. Herkes de kelime falan.
Evet. Şöyle böyle yaptım. 25
Ses kısıtlı yani.
Ben dedim hocam lütfen sıfır verin. Kaynak böyle şey yapalım. Ben dedik hocanın talimatı.
Sen de yani.
Ben dedim hocam sıfır verin dedim.
Ben de öğrenmedim. Bana şey yapmadım.
Sen de mi kelime attın?
Bakalım kulak.
Ben kendimi yapmadan olmak istiyorum.
Ya bir iki asa çeviriyor, yanındaki kemiğe de götürüyor. Saçma. Yok öyle yapıyoruz, görmüyor musun işte? Yine de oluyor ya.
Benim bir arkadaşıma demiş. Seni şeyin kolunu 2 megabaytlık tutuyorum demiş.
Oha. Ben
2 megabayt de.
1,5 milyon satılık bir ilk bulasını
Gerçekten ya.
1,5 milyon satılık
Ben
bir şey.
şöyle şeyler denemedim ya. Bilmiyorum, ben denemeye korkuyorum. Denemedim öyle şeyler.
Ben ikinci de böyle, üçüncü de 12 master denedim yaptım. Orada da bayağı uzun sürdü. 5 tane yapmışız.
Yani zaten 5'ten kısa sürmemesi lazım da.
Bayağı uzun sürdü ya.
Z'lere geçince daha yavaşlıyor. Çünkü Z'ler arkada bekliyorlar ya, onlara istek gelse de mecburen bekleyecekler.
Çok yavaş yavaş böyle pişler kafanı yersin ya. Çıldırdım. Ve çok zorladı beni. Hani yaşlandım. Çok yaşlandım. Ben şu an sıralarım kendimi. Ama olmuyor. Patladı böyle. Vurdum kafayı. Abi bugün eve gittik 9-10 saat
Seçmedin mi?
aynen.
Bir de şimdi sistemde bu notların yaptıkları sistemde de kalmak istemiyorum. Gerçekten çok kötü.
Kaç var?
Hiçbir fikrim yok.
Teoride her şey yapıldı. Teoride her şey yapıldı.
Zaten böyle şeyleri yaptım. Gerçekten bilemiyorum.
Ama çok güzel rapor yazardım. Mesela 2 saat yazı yapıyordum. Okumuyorlardı. Keyifli. Neler var hayatım? Operasyon.
Harika ya. Online olsaydı sana keşke gerçekten. İşte bilmiyorduk o zamanlar.
Keyifli bir yüzden değer yaşadım. Ömrümde değerli.
Bize geçersin.
Şimdi orada bir entegre olacak ve entegre de sanırım.
Tekrar keyifli ya.
Fazla yoğunluktan dolayı.
Yok artık senin.
Yapıyorsa okur. Yapıyorsa okur.
Aynen
Yoksa
ya.
o süresini okur ya.
Final zamanı falan okur.
Şimdi de sistem böyle çok gece çıkarsa pek hoş olanı pek hoş olmaz.
Benim için daha yorucu.
Kardeşim ölüm mesajı getiriyorum sana, yanlış yere vuruyorum ya.
Çok güzel. Anladın mı? Depremde mi?
Ama yani öyle bir konu olsa ki Allah bana versin.
Normalde bir şey girmiş gibi hissediyorsun ama o atmaktan yapıyorsun.
Reflekt dosyasında yaşadım.
Her yere gitmedim.
Ne?
Kanka şunu tutsana, çöp alsana bana.
Niye?
Lazım ya.
İstemedim.
Çok mu üzücüsün?
Hiç istemedim.
Dokunmayın arkadaşlar.
Kanka çok güzelsin.
Önce
Çok
dokunmayın.
kasıyor var ya.
Dokunamazsın.
Yok ama ne zaman tutuşum.
Dokunamazsın bana.
Keyifli. Dokunamam.
Tutamazsın.
Aa tamam.
Tutamazsın.
Fazla bak kaşıya başladım.
Tutamazsın.
Mümkünse.
Bana sen 5 lira veriyorsun bana.
5 lira vereceğim mi?
5 lira vereceğim.
Anında tek.
Şöyle yaparsın.
Böyle yapma.
Tamam şöyle.
Onu yap. 5 liraya değmiyor.
Kaçırdır mı yapıyor ya? Parmağını birazcık hala yapıyor.
Hadi ya. Keyifsiz.
$5 verirse bekliyorum.
O 5 dolar verirsen ben de yaparım.
5 dolara aynen.
5 dolar bir gün
5 dolar
çalışıyor
yiyelim.
insan.
5 dolar yeriz.
Sabah sabah başım
O şey 4 yıl yaşanmış.
Söylemek isteriz. İlk arkadaşım. Bu yani. Korur. Ve bundaki ilk arkadaşım. Jim'in sesi olmanız tek olmadı.
Çözeceğim. Şey gibi. Çekicileri yapmadan yani. Bana yollarını
Öyle mi oldu? O zaman mı?
Valla iki dünya arasında.
Şey geçtik mi?
Of!
Ama update desek mi? Ya yapalım. İşte.
Ben de sonra işe yarıyorum.
Nerede şey yapalım?
Neden?
Ama yer olsa lazım. Diğer bir yer olsa lazım. Bir ara al. Neyse bir sonraki listeye aktaracağız.
Özellikle yine ezbeyi düşünüyorum.
YS'de ben sana 5 dolar.
Yes, hayır. Çıkışı yes.
5 dolar veriyorum.
Nereden?
Bulur valla. Bulmuştum.
Burada online ders tutmakta mı ya?
Ona bıraktı mı?
Nerede bunu yapıyorsunuz? Zaten ne yapıyorsunuz? Nereden? Hani yesene kaçar
Oraya bile geçip
Hocam yapımıyla attın.
Evet.
İmzalamadım da.
Derse geldin mi?
Arada geldim.
Yok olmaz. Okay, so swapping is something that is unavoidable if the memory is not enough. I have to do something about it if the memory is not enough. Then maybe one of the things is, what did I say? If I am causing crashing, then I will have to kill one of the processes. So I have more memory, but killing something is not nice, right? I have a process running and somebody is killing it, I don't have any knowledge about it, and etc. Maybe I can wait. Maybe waiting for a long time is better than my process getting killed. So the answer is swapping. If the memory is not enough, then trashing is unavoidable. So what is swapping? Write the entire program out to the disk when it is blocked. Okay. So when my program is blocked, when it is not running, so write the whole program to the disk. So I release all of my pages, and other programs can use that memory. When the context switch happens, okay, so this time the context switch is going to be much more expensive because I have to read the data back in, and I have to load the whole program, probably at a different address. And when my program is ready, then I can run. Okay, so apparently this is a solution, but it consumes lots of I/O bandwidth, and that's going to make my context switches a lot slower. And the other thing is this: I don't have just two programs in my memory. Okay, I have many programs running at the same time. I have many programs blocked, waiting something to happen. Okay, so which one of those programs should I write it to the disk is another decision that I need to. Okay, I need to check. So that's the question. One question. Remember, we are trying to answer all of these questions under this heading. Okay, design issues. These are the issues that we have ignored, that we did not look at, where we said that we are going to solve this later. And most of the time, actually, we are not solving any of those. We are saying that these are the problems that the operating system has to solve. And every operating system has a different way of solving these problems. And sometimes they just ignore it. Okay. So let's look at this one again, swapping. If I am going to swap a program to the disk, which process should be swapped out? It's not a good idea to swap out all the blocked processes. That would be too slow. Choose a few of them, okay? But how do I make that decision? Operating systems makes that decision by looking at the size of the program. If the program is very small, then there is not much point in swapping that small program out because I am not going to gain much, okay? How about the priority? Should I swap out high priority interactive process to the disk? Maybe no. And how about the history? That process is blocked for a very long time. Maybe I should swap it out. So my decision is going to be low priority tasks if the size is high, large. And for the history, it did not run for the near time. Okay, so that's called swapping, controlling the swapping. Okay, and the other thing is that once the processes are swapped out, when do they come back in? Well, remember we said that these are blocked processes. When they are not blocked anymore, when the data they are waiting for is ready, should they immediately come back or should they stay on the disk for more time? Okay, so this looks like, remember our scheduling tasks. Okay, our scheduling algorithm, the scheduling algorithm says that who is going to CPU now, right? That's the task of the question of the scheduling, okay? We have a similar question now. Who is going to stay on the main memory, okay? So that's kind of a second scheduling question. Two-level scheduler. One for the ordinary CPU scheduling. The other one is for the memory scheduling, okay? Who is going to stay on the memory and who is going to stay on the disk? Okay, that's the second level. The first level, that's we already know who is going to use the CPU now. Okay, so it makes sense to of course keep those low priority jobs, large jobs, and not recently used jobs on the disk. The scheduler will make that decision. When the time comes, I am going to load some of them to the memory. And when I'm doing this, I am going to look at this one: CPU utilization, throughput, okay, those kind of stuff, depending on my operating system type. Okay, if I have a mainframe, of course, throughput and CPU utilization is important. But for a mobile computer, maybe the interactivity is better criteria to look at. So maybe the priority or the interactivity is a better feature to look at. So the controlling swapping is not an easy thing. It is as complicated as CPU scheduling, okay? But there is no escape from it. I mean, if we are going to do this multitasking systems, more than one program running at the same time, okay? I have to risk of loading many programs to my computer, and I have the risk of having memory trashing. Okay, so to solve this trashing problem, either you have to terminate one of the programs, that's a bad thing, or you keep swapping. Okay, write the entire program to the disk and wait until the time is right. Okay, good. So again, just a single slide. If I wanted to go into detail in swapping, okay, I can spend 2 or 3 weeks on it, okay, because as I said, this is as complicated as CPU scheduling, okay, but I am not going to do that. This is just an introductory course about operating systems, but you should know about this problem. Swapping is a critical operating system problem. That's one of the design issues of the operating systems. How do we control the swapping? The other one is the page size. Okay, the other one is the page size. Let me try to hide the answer. Okay, like that. Okay, with the large page sizes, it is nice because if my pages are large, then my page table will be small, right? Because if I have a memory of 10 to the power, not 10, 2 to the power 30, and my page sizes are 1 kilobyte each, that means what? I will get 1 mega elements of page table, okay? But if I make it 2 to the power, let's say 4 kilobytes, then it's going to be 256,000 elements in it, right? So it is going to be 2 to the 18. Okay, so that's of space. So it is like 4 times more memory between these two. Okay, so larger the page size is, the better. But what is the downside for the large page sizes? If I allocate a page, you cannot allocate half a page or 1/3 of a page. You have to allocate a page. Okay, so you have to waste some part of that page. But you might say that if this is my process, if my process is 13 kilobytes, okay, and if my page sizes are 4 kilobytes, then that means what? I need to allocate 1, 2, 3, 4. Okay, this is 13, has to be 13. So I need to allocate 14 kilobytes. I need to allocate 16 kilobytes, sorry, but I am using 13. So that means what? I am not going to use this 3 kilobytes of the last page, right? So it is wasted. So on the average, 50% of the last page will be wasted. If my page size is large, then this wasted memory space is going to be large, and that's I don't like. Okay, so let's write this equation. Equation is this: if I have a process size of S, my process size, let's say, is again 13 kilobytes. Okay, and if my page size is 4 kilobytes, S over P, of course, I am going to take the ceiling of it. So S over P is going to be 4 times E. E is the bytes for each, number of bytes for each table entry. Let's say in my table, page table, I need to keep 100 bytes for each page table entry. So S over P times E will be the page size. I need to use this much of memory for my pages. Okay, page table. That's one thing. The other thing is that for each process, okay, for each process, I am going to waste the half of the last page, so P over 2 will be wasted. So that's the overhead of using paging for a process, single process. Okay, process size over P times E plus P over 2. In this case, I know the process size, I know E, I am trying to optimize E. Okay, I am trying to optimize P. I don't know the value of P. Should I make it 1 kilobytes or 2 or 4 or 8 or etc., right? So I am going to, by the way, I mean the page sizes has to be the power of 2. It has to be either 2 to the power 0, 2 to the power 1, and etc. 2 to the power 0 is not a good idea. Each byte is a page. Theoretically, it is possible, but there is no point in making each byte a page. So we usually talk about things like 1 kilobyte or 2 or 4, okay, or 8, or it goes like that. Okay, so I am going to make that decision. So I need to optimize this value. To optimize a value analytically, what we do is just take the derivative with respect to P. Okay, take the derivative with respect to P and make it equal to 0. Okay, and solve the value for P. So take the, okay, so I do this derivative of O with respect to P is going to be, okay, tell me what to do. Let's do the easy part now. It's going to be, this one is 1 over 2, right? And plus, how about this one? This one is S times E times P over minus 1, right? That's what's going to be, okay? So it's going to be P over minus 2 and S times E, and I guess it will be minus, right? It's going to be 0. Is it correct? Did I do it right? Say yes or no. This is P over P to the power minus 1. And if I do this, it will be P, okay, P to the 2, or P to, why don't I do it this way? P2. Okay, if I make it this way, right? Yeah, okay, it is going to be, it's going to be P square is equal to 2 times SE, right? And here P is going to be square root of 2 SE. Okay, so take the square root of S times E. E is the size of the page table entry, S is the size of my process. Multiply it by 2 and take the square root of it. This is your optimal page size in terms of minimizing your overhead. Of course, I am ignoring the other factors such as larger pages are more expensive to read from the desk and write to the desk. So I did ignore the CPU, the I/O wait time for the page size and etc. This is only for the memory usage overhead for the pages. And this is what the book says. Okay. So we do this kind of stuff in operating systems. Analytically solve some equations to get the better page sizes. It is nice, but these kind of solutions are not usually very practical. The practical solutions are usually what? Instead of doing this, what do I do? Instead of doing this kind of analytical solutions, closed form solutions based on the optimization theory or the derivatives, what would you do?
Can we use simulations?
What?
Simulation.
What do you mean relation?
What?
What is relation?
Simulation.
Oh, simulation, yeah, of course, exactly, yeah. Running a simulation is a better idea because with the simulation, you are looking at the end result. You can say that I am going to choose a page size so that it maximizes the usage of the memory and the CPU at the same time. Okay? So with a page size of 1 kilobytes, this is my CPU utilization, this is my memory utilization, this is my I/O wait time for the page faults and the number of page faults, etc. And let's make this 2, let's make this 4 and 8 and etc. If you simulate in a realistic way, then it's a better way of choosing your page sizes. Okay? Of course, this helps, this is nice, but choosing the page sizes or any other operating system parameter is done by the way of simulations. And in fact, well, for the page sizes I can't do that, but for some other parameters, while your operating system is running, okay, it's kind of you are simulating it, right? It's kind of a simulation environment. Even in the real world, when I'm running this operating system on this computer, I see my PFF values, page faults, I see my CPU utilization, I see my memory utilization, it is all here, right? Although this is not a simulation environment, this is the real environment, I have all these values. If the things are not going right, I can change some of these parameters, but of course you can't change the page size on a running system. That would be too complicated. But I can change, maybe remember those A and B values here. A and B values. Okay, if I see that I am causing too much trashing, too much PFFs, that means what? Maybe I am not keeping enough number of frames. So maybe I should increase, maybe I should just decrease this value a little bit A. So dynamically I can allocate, dynamically I can change these values, A and B. But I can't do, of course, I can't do that dynamically for the page size. I should run simulations for the page size. Just one example of design decision. Okay, another one is this. Okay, sometimes we get lots of help from the hardware, and some of the hardware, including the Intel hardware, is nice enough to provide us 2 separate spaces, memory spaces, for instructions and the data. Okay, for instructions and say that data. It say that, okay, you are going to have a virtual space of 2 to the 30 instruction space and 2 to the 30 data space. Okay, so I'm going to keep the I and D spaces, instruction and data spaces, separate. So now you will have, instead of 2 to the 30 bytes of virtual space available, you have 2 times of that. Okay, 2 times of that. That's a nice thing. That's one thing that we like. The other thing is that keeping these I and D spaces separate. Okay, this is the picture. Previously, I had to keep all of my program and the data in this virtual space, virtual address space, 2 to the 30 bytes. Now I have 2 separate spaces. Each one is 2 to the 32. Okay, this part is unused for program. This part is unused for the data space. And you might say that, well, these are wasted. No, it is not wasted because I am using paging, right? With the paging, these pages are empty, so they don't use any space in my memory at all. Okay, so I space and this space. So in terms of using, on a 32-bit computer, now I have 2 times the space for each process. That's nice, but nicer thing is this. Let's think about a fork operation, fork system call. When I make a fork system call, remember what the fork does? It copies the parent process, right? It makes the exact same copy. So that's nice. So how do you make the same copy of the process? You copy the process byte by byte. But if you separate the I and D spaces, then this would become possible. I have 2 different processes in my process table, but both of those processes, since I forked one of them from the parent one, okay, they are pointing to the same I space, instruction space, because their programs are the same, right? They are running exactly the same program. Their data spaces are different because their data will be different. They modify different parts of the memory, but their instructions are exactly the same. So what did I gain? I saved lots of instruction space after the fork operation. Okay, I saved lots of memory after the fork operation. So this separation of instruction and data space is something very useful in this case, especially for the fork. Okay, or maybe I shouldn't say just only for after the fork. Maybe the pages that are read only. If a page is read only, okay, after the fork I don't have to copy that page. Keep using the same page. Okay, in my page table both of the processes are pointing to the same page. That's a nice thing. Okay, pages that are read only, such as program text, can be shared, and after the fork I am using this property. Or remember, I have dynamic link libraries, DLLs, dynamic link libraries. For example, the dynamic link library of the C programming environment or C++, for example, the classes that I use from the standard template library. Many programs are using the same classes. Okay, I have 3 processes, they are using the same classes, but I don't have to replicate the code for each program. I put them, okay, I put them in the same shared library like that. My process 1 and my process 2, they think that they are using their own version of that library, but in fact they are sharing the same library on my memory. Okay, because sharing the pages are now possible with the paging, especially if you separate the instruction space and the data space. I know that this process is not going to modify anything inside this because this is an instruction space. This one will not modify anything because it's an instruction space or it's a read-only space. Okay? So shared libraries are handled this way. Once the DLLs are loaded to the memory, many processes can use the same DLL pages without copying them. So that's a very nice property of this paging, and we like this property of paging a lot because it makes things a lot more efficient. Instead of statically linking with your runtime libraries, you dynamically link them, and during the runtime, operating system will tell you where you find your pages, and you just include those pages in your page table and you'll be done. That will be it. And sharing will be automatic. Sharing will be automatic. Okay? Sharing will be automatic. That's the other thing. Okay. Let's look at this problem. After the fork, I said that I am going to share the instruction part of the program because it is exactly the same. I cannot share the data because each program should have its own data. But my observation is most of the time I change only this one or maybe this one or maybe this one. Okay? Most of the time I don't touch the rest of the data pages. I just read them, I don't modify them. Okay? So there is no reason for me to copy these because this is exactly the same copy. I am not modifying these. Okay? Since these are exactly the same copies, I am not modifying them. Maybe I should share them too. Okay? So there is a policy, there is a technique to do that. Okay? After a fork, only the pages that are actually modified need to be copied. But how do I know which pages are going to be modified? Well, there is this method of modifying pages. It's called copy on write. Okay? At the beginning, this is what you do. At the beginning, I have only one instruction space and one data space for both of these processes. Okay? Both of them are sharing the program and both of them are sharing the data. Okay? I copy the data pages only if I modify them. Okay? If I copy, let's say, if I modify, let's say, this page, if I modify this page, then I copy it only I have to modify them. That's called copy on write. Okay? So this way I end up using lots of common shared pages between two processes after the fork. Okay? Of course, this is more difficult to handle for the operating system, but if you handle it right, you will save lots of memory. Saving lots of memory is good for obviously for the memory, but saving lots of memory is good for your cache, is good for your context switch, because when you do the context switch, remember, most of your page table entries will stay the same, and you will not invalidate your cache. Some part of your cache will stay the same, and etc. So it has positive effects in terms of overall system performance, both memory utilization and the CPU efficiency and utilization. Okay, so this is an important technique. It's called copy on write. Of course, you need again hardware help for this. If you say I am going to modify this page. When you say that, the hardware should have a way of causing some kind of an interrupt, saying that you are modifying a shared page. Okay, so you need to copy this page yourself. I need to get some kind of a interrupt from the hardware. Otherwise, this wouldn't be possible. This wouldn't be possible. Okay. So these are the story about the shared pages, and shared libraries are kind of the same. Instead of you know this, right? I mean, the static binding and the dynamic binding. Okay, statically linking your libraries or dynamically linking your libraries. If you have a library that you yourself is going to use only, nobody else is going to use it, maybe statically binding it, statically linking it is okay. But if you have a library, many processes are going to use that library, then DLLs are the answers, okay? And I have many DLLs loaded in my computer. If I can show you some of them, where is my, just, okay, open up one of them. I'm going to show you the okay, some of the DLL stuff. Do I have it? Couldn't find it now. Okay, get this one, and you will see that CPU is here. You will see that some of the DLLs are, well, it looks like I am not using, none of my DLLs are using any CPU now. Couldn't find it. Well, I did not get it separated from the EXEs. Maybe this way. Dynamic link libraries. No, these are all executable stuff. I couldn't find it, sorry. If you load your DLLs and they are shared, they will be using CPU, lots of CPU. But since they are shared, I can load them up in my cache. And when I context switch between two processes, since they are sharing the same DLL, then that will be a better context switch time for me because I am not going to invalidate my cache. Okay, so shared libraries are paged, and of course I need to do this position independent code. Okay, this one, okay, for the process one, this is my virtual address space 2. This is the virtual address space 1. This one will think that my shared library is at this position. This one will think that my shared library is at this position. Of course, if I have absolute addresses, for example, if there is an instruction jump to position 40K, and the same thing is jump to position 40K. Well, if you include these kind of absolute addressing instructions in your code, that's not going to be good. Okay, so you shouldn't say jump position 40K. You should say jump relative minus 20K. So jump relative to my address, maybe to 20 kilobytes before me or 20 kilobytes after me. So all the addressing should be position independent. Don't use any position dependent code. Don't give any absolute addresses. Well, how can you say that? How can you for a variable, how can you specify its position without giving the exact position? Well, use local variables, right? When you use the local variables, you are using the stack. When you use a stack, you have your own stack. Okay, this process has its own stack, and this process has its own stack. I don't keep any data here or there or there. I keep my data on my stack, and this code uses my stack without knowing where that stack lives actually. Okay, with the stack, I always reference my stack positions as stack pointer -8, stack pointer -12, and etc. So that's called position independent code. So you are saying that, well, you formed your own, you have created your own dynamic link libraries, right? You might say that, well, I never have written position independent code, but the compilers do that automatically. Compilers say that if you like this to be a DLL, then I'm going to create position independent code for you. It's the responsibility of the compilers and linkers to do that. Good. Any questions? Again, shared libraries is another design decision that you need to make for your memory management. Another issue that comes up most of the time is very useful features of operating systems, mapped files. Okay, operating systems has this nice feature of mapping a whole file, a secondary storage file, to a part of the disk, to a part of the memory, sorry. If this is my virtual memory for my process 1, okay, I can ask the operating system, map this disk file to this position. So whenever I read a byte from this position, I am actually reading bytes from this disk position, actually disk file. Okay. So you might say that, well, this will be very slow. Yeah, it will be very slow, but it's a nice way of using your disk like a memory, and without realizing that your data is on the disk. Okay, so it's called map files, and instead of doing a regular file input output, your code is running a regular memory based instruction. Okay, instead of doing reads and writes from the disk, you are using your regular instructions. Okay, and basically your shared libraries, your DLLs are actually like that. Okay, your DLLs are actually like that. Your operating system maps, your DLLs to some part of the memory, and your programs are using those pages of your memory, and it is all done through this feature of mapped files. Okay, mapped files. And if two or more processes map onto the same file at the same time, they communicate over, or they share the same DLL file. Or if I let those processes modify those shared pages, then I am doing inter-process communication. Remember what we said about the inter-process communication between the threads? Communicating between the threads is easy because threads are sharing the memory by default. They have to share the memory. That's the idea of the threads. How about the processes? Processes usually do this. They share the same part of the memory, okay, not just for the code but for the data. Okay, so if I write some data to that part of the memory, it is shared by some other processes, then I can communicate with the other processes with that part of the memory. Of course, there will be race issues. Okay, there will be race conditions. For that, we already know how to do inter-process communication, monitors and semaphores and those kind of solutions. Okay, so these are the map files, and in both Windows and Unix, you can say that, okay, make this file part of my memory. Whenever I read this part of the memory, actually I am reading and writing to that file, and you can do that. And it is easy to do that with paging. Good. Okay, I think I am out of my time for today. I will stop at this point, and I will tomorrow. I think I can finish up this chapter. Yes, I can finish up this chapter. And next week we are going to start talking about the third important module of the operating system, that is the file systems. Okay? See you tomorrow.